Welcome back, everyone, to the Classification with Text Data lecture series. In part 2, we're going to discuss building models, that is, building several machine learning models, as well as creating a function to compare them all. Let's go ahead and get started by continuing where we left off last time. All right, here we are at the notebook where we left off last time. We have our X training data ready for the model to be fit on with this TF-IDF, the term frequency inverse document frequency form, in a sparse matrix. Now, when it comes to text classification tasks, I would always encourage you to try several models. Now, obviously, 𝑵𝒂𝒏𝒈𝒄𝒆 is a very popular model to choose for text classification, but I would always suggest that you try multiple models and compare the results between them. So let's try a bunch of them. We're going to say from sklearn.𝑵𝒂𝒏𝒈𝒄𝒆 import multinomial NB. And for all these models, we're just going to run them with the default settings, and then maybe you could choose to do some more grid search cross-validation to try to tone or tune those hyperparameters. So we're going to say NB is equal to an instance of multinomial 𝑵𝒂𝒏𝒈𝒄𝒆, and then say NB.fit, and we're going to fit to that training data. So fit to that training data along with our training labels. So we can go ahead and fit a multinomial 𝑵𝒂𝒏𝒈𝒄𝒆, and let's fit a few more models. Let's say from sklearn.linearModel import logistic regression, and we'll say log model is equal to logistic regression, and then we're going to say this log model dot fit to, again, xtrain, make sure we spell that correctly, xtrain TF-IDF along with ytrain. Now, if you run this, you may get a warning that basically tells you to increase the number of iterations. So let's go ahead and do that. We'll say max iterations, and we've seen this before when we talked about logistic regression earlier. We'll go ahead and give it some more iterations in order to perform that stochastic gradient descent. All right, for our final set of models, let's start using some support vector machines. We will say from sklearn svm import, and I'm going to import svc. And then just for clarity, we'll also import linear SVC, which recall is actually the same as support vector classifier. It just hard codes the kernel to be a linear kernel. So we have the default SVC as a radial basis function. So I can say RBF SVC is equal to SVC. And I'm not going to perform a grid search for this particular project, but obviously you could if you wanted to. And then we're going to take this radial basis function, support vector classifier, and I'm going to fit it to that training data along with ytrain. So go ahead and run that, and I'll do the same thing for the linear SVC. So it's going to be an instance of linear SVC, and then we'll say linear underscore SVC. Go ahead and fit that to our xtrain TF-IDF along with ytrain. Run that. Notice the linear model is using a much simpler kernel, that linear kernel, so it trains a lot faster than the radial basis function. And we'll have to check out their performance. So we have a bunch of fitted models. What would be nice is for performance evaluation purposes, we just have a nice, easy to use function. And I would highly encourage you in real world projects where you're comparing a lot of machine learning models that you automate this task of creating a nice function to basically give you an easy to read report. And that's what we're going to try to do here, kind of in very basic, simple terms. We'll say from sklearn.metrics import, and we'll import plot confusion matrix as well as the classification report, which are really the two main things we need to view to understand our model. So I'm going to create a reporting function that takes in a trained model, and then it's going to create predictions from that model. So we'll say model predict off x test TF-IDF, and then what we're going to do here is print out a classification report. Takes in ytest and the predictions created, and then we'll also plot the confusion matrix, which takes in that model, the xtest TF-IDF, and it's also going to take in ytest. Okay, so we have this easy to use report function, which means I can directly pass in any fitted model, like the 𝑵𝒂𝒏𝒈𝒄𝒆 model we created earlier, and just run report NB, and I get to see the classification report. Notice it doesn't do too good on neutral, but really what we want to focus on is how well is it performing on the negative reviews. Because for the way we frame this problem, we want to make sure our customer service agents can get to those negative reviews or those negative tweets. And you'll notice it actually performs pretty well at catching the negative tweets. In fact, there's only 10 negative tweets that it mislabeled as neutral or positive. But the major caveat to this is that it actually labels quite a few positive and neutral tweets as negative as well. So notice here that while it found pretty much every single negative tweet, it actually labeled most tweets as negative, which is why I was able to catch those. You can see here we are also classifying many neutral tweets, 524 of them, and 399 positive tweets, all as negative. So really, it looks like this naive Bayes model happens to push everything to just be classified as a negative tweet, so it doesn't actually have that great of precision and recall, actually recall specifically for neutral and positive. So you can see right here, really poor F1 scores on neutral and positive, which is what's leading to this good performance on negative. So that's how we can read this in, which is why it's so nice to have the combination of the confusion matrix with classification report. So the next model we want to take a look at was a logistic regression model. So we can say report, we'll say log model here, run that. Okay, looks like our F1 scores are performing quite a bit better, and we can scroll down here to see how many we're missing. So in this case, our F1 scores across the board are performing a lot better. Yes, there's definitely a lot more tweets that are negative that we're not catching. So it looks like we're not catching 122 in total, but we're actually able to classify between the three classes a lot better. And recall that really what we care about is negative versus everything else. Okay, let's try out those support vector classifiers. So we're going to start off with that radial basis one, RBF-SVC, run that. And keep in mind, it may take a little bit of time to run those predictions. And F1 score, not super great, not super different from logistic regression. Again, kind of a similar performance to the logistic regression model. And then let's check out the linear support vector classifier. Run that. And again, very similar performance to what we saw here. So definitely this would be a good time to take a look at the support vector classifiers, since that gives you a lot more hyperparameters you can tune versus something like logistic regression, where you really only have that C value you can end up tuning for regularization. So at this stage in the process, you would want to begin performing a grid search against something like a logistic regression for that regularization, or a support vector classifier experimenting with different values for its hyperparameters. Something else we didn't really explore here are tree-based methods, but keep in mind this feature set is technically huge, which may not be ideal for something like a tree-based method since it ends up splitting on many features. Okay, so if we've decided that we're going to go with, for instance, linear SVC, what would be a good call is to finalize this with a pipeline that can be then deployed on new tweets. So how do we actually do this? Luckily, scikit-learn makes it simple for us. We say from sklearn.pipeline import, have that here, import pipeline, and then we're going to say pipe is equal to pipeline, and then we're going to pass in the steps that we want. So the first step is to actually perform the vectorization. Keep in mind, this pipeline is going to be fed in raw string tweets. So the first thing we want to be able to do is say tf-idf, and then we're going to pass in the tf-idf vectorizer. And then the second stage, we're going to label, let's just say SVC, and we'll have it be equal to an instance of linear support vector classifier. So the whole reason for doing this is that now we have a pipeline that will directly vectorize for us, as well as have this support vector classifier ready to go. So this is essentially model deployment. So because this is model deployment, we're going to assume that we're satisfied with this performance here. And once you're satisfied with your performance, when you're ready to deploy your model, you're going to have to retrain it on all the data. So we take this pipe, and now I'm going to fit it on the entire data set. So I'm going to grab the original X here and the Y, and I'm going to go ahead and train that. And recall that X is actually the raw strings. And the reason it can take it is because the pipe is performing that vectorization first before fitting that support vector classifier. So I can pass in X and Y, which means now my pipe object is ready for a tweet. So I can say pipe predict and then pass in just a single tweet. Note the shape here, so I'm passing it in as an item of one list. So I can say something like good flight, run this, and it predicts it as positive. Let's try kind of a more obvious one, bad flight. It thinks it's negative, and let's try just okay flight. and it thinks of it as neutral. Perfect. Obviously, these are kind of cherry-picked examples here, but overall, it's performing as expected. Great. Okay, thanks, and I'll see you at the next lecture, where we begin discussing a project for you to tackle on your own.